You can almost imagine the Earth shivering, even though it is a world of stone and water and drifting clouds, because every 100,000 years, almost like clockwork, it plunges into a cold so deep that entire continents disappear under ice a mile thick. And for a long time, no one understood why a planet that orbits a warm star would freeze in such a rhythmic, predictable way. The mystery feels almost supernatural at first glance, as if the Earth hides an ancient timer buried beneath its crust, yet the truth is both stranger and quieter. A delicate chain of celestial nudges, tiny variations in sunlight, and slow feedbacks that build over millennia until the world tips into a deep freeze. And because this tale belongs to deep time, we begin by settling into its slow pulse, summaries whispering ahead while details unfold gently, so the listener can rest while drifting into the sweeping rhythm of Earth's frozen cycles, understanding how orbital changes, shifting sunlight, ice sheets, carbon dioxide, and ocean rearrangements combine to create the planet's great repeating winter. The story begins hundreds of thousands of years ago, long before agriculture, before writing, before even the rise of Homo sapiens as we know them, when the planet's climate was ruled by forces no human eye could see. And yet the patterns were already set. Long stretches of cold glacial periods, lasting roughly 80,000 to 90,000 years, interrupted by brief interglacials, warm intervals like the one we live in now, lasting perhaps 10,000 to 12,000 years. Each cycle rose and fell with the slow reliability of a tide, carving valleys, shaping coastlines, and determining whether mammoths or forests would roam across Europe. These cycles were so vast in duration that generations lived and died without noticing any change, yet over ages the transformation was unmistakable. Glaciers expanding across Canada, ice domes crushing Scandinavia, sea levels dropping more than 120 meters as water locked itself in ice. Something profoundly rhythmic was happening, and the puzzle only deepened as scientists sampled ancient ice cores, revealing layers upon layers of frozen time. Those frozen cylinders extracted from Antarctica and Greenland are like diaries written by the planet itself, storing tiny bubbles of ancient air and grains of dust that reveal temperatures, greenhouse gases, and atmospheric changes across hundreds of thousands of years. When researchers plotted those data across time, a clear beat emerged. These massive ice ages came in cycles centered around roughly 100,000 years, repeating with surprising consistency over the last million years. And this peculiar rhythm didn't align with Earth's spin or its seasons, but instead hinted toward the heavens, suggesting the answer lived somewhere in the geometry of the planet's orbit. It was soon recognized that Earth doesn't circle the sun in a perfect, unchanging path. Instead, it moves through cycles of wobbling, tilting, stretching, and shifting that unfold quietly over tens of thousands of years. These slow astronomical motions, known today as Milankovitch cycles, affect how much sunlight reaches certain parts of Earth at specific times of year, especially the high northern latitudes where ice sheets are born. The shock, once understood, was how tiny these orbital changes actually are. Fractions of a degree in tilt, subtle shifts in the shape of Earth's orbit, slight changes in the timing of when Earth is closest to the sun. Individually, they seem too small to matter. Yet, over tens of thousands of years, these slight adjustments act like the soft push that starts a massive swing moving, setting off feedbacks across air, ocean, and ice. When summer sunlight weakens just enough in the northern hemisphere, winter snows fail to melt completely, accumulating year after year until glaciers take root. Once ice begins to grow, it reflects more sunlight, which cools the planet further, encouraging more ice, which amplifies cooling again. Thus, a chain reaction begins, slow at first, then relentless, pulling the Earth deeper into glaciation. What makes the 100,000-year cycle so mesmerizing is how it ties together several overlapping rhythms. The 41,000-year cycle of Earth's tilt, the 23,000-year cycle of precession, the wobble of Earth's axis, and the 100,000-year cycle of eccentricity, how stretched Earth's orbit becomes. For reasons scientists are still refining, the eccentricity cycle eventually became the dominant pacing driver after about 1 million years ago. Before that, ice ages followed a 41,000-year pattern driven mostly by tilt. But as global conditions changed, possibly due to long-term cooling of the planet, shifts in ocean circulation, or declining atmospheric carbon dioxide, the climate system became more sensitive to the eccentricity cycle. In other words, Earth slid into a new mode of glacial rhythm, one that matched the larger eccentric cycle and produced the massive ice ages recognizable today. It is remarkable that a planet's freezing fate could depend on something as delicate as annual sunlight distribution over Canada. But the evidence is clear. The critical trigger zone is between about 60° and 65° north, where summer warmth determines whether winter snow melts away or lingers. When the orbital configuration weakens those northern summers, ice begins to accumulate, and once accumulation starts, the planet is carried slowly but surely toward its next deep freeze. This means every glacial cycle is born not in the darkness of winter, but in the subdued brightness of summer, a season so slightly dimmed by orbital geometry that snow quietly refuses to disappear. By the time the process is truly underway, humanity hasn't entered the story yet. Instead, Earth is sculpted by forces older than our lineage, the advancing of white sheets that crush forests, the grinding of mountains into dust, the migration of animals across exposed land bridges, the shifting of winds as continents cool unevenly. And through it all, the cycle remains steady, repeating with a patience that only geological time can maintain. As we settle into this narration, you can imagine that first hint of snow that doesn't melt, and the faint beginning of a future world locked in ice. The story that follows will trace every part of this cascade: how orbital shifts shape sunlight, how ice amplifies itself, how oceans inhale carbon dioxide, how dust clouds grow, and how the planet eventually warms again and melts the ice in a rush of catastrophic beauty. But for now, we end this section standing at the doorway of the cycle itself, with Earth poised on the edge of the first cold step, guided by nothing more than gentle changes in the cosmos. Earth's path around the sun is not a fixed circle carved in the sky. Instead, it stretches and relaxes over time, transitioning between slightly more circular shapes and more elongated ellipses in a cycle that averages around 100,000 years. Even though this change in shape, called eccentricity, might seem too subtle to influence something as dramatic as the freezing of continents, it matters because it alters the intensity contrast between the seasons and changes the timing of Earth's closest and farthest points from the sun. For a planet delicately balanced between warm and cold feedback loops, these gentle tweaks are enough to start nudging climate patterns in new directions. When Earth's orbit becomes more eccentric, there are periods when the planet swings closer to the sun at one part of the year and farther away at another, creating slightly stronger seasons in one hemisphere and slightly weaker ones in the other. But the deeper mystery is that this effect is not symmetric. Because land masses absorb and release heat differently than oceans, and because the northern hemisphere contains more major continents, changes in sunlight distribution there have far greater impact on global ice formation than similar changes in the south. The orbit may stretch only a small amount, just a few percent deviation from circular, but over tens of thousands of years, these small variations shift the background conditions of seasonal energy, priming the climate system for either survival of summer snow or its complete disappearance. Eccentricity by itself does not create ice ages, but it acts as a master scheduler for when other orbital factors, tilt and precession, will exert the greatest influence, aligning their effects to produce either cooling or warming. The orbital dance is made even more complex by the fact that Earth rotates while moving along this shifting path, and the rotational axis is not fixed either. This means that the intensity of sunlight at any given latitude changes not just year to year, but over cycles spanning tens of thousands of years. When eccentricity is high, precession becomes more important because the timing of when Earth is closest to the sun, its perihelion, can dramatically enhance or diminish the power of summer in the north. For example, if the northern hemisphere's summer occurs when Earth is farthest from the sun, the resulting cooler summer can allow more snow to survive, even if the winter is relatively mild. If that pattern repeats for thousands of years, ice begins to accumulate. This interplay between orbital shape and the timing of the seasons is subtle yet powerful, setting the long-term stage for glacial expansion. And so, the idea of the Earth's orbit as a quiet architect begins to take shape. It does not build ice with brute force, but by adjusting the background lighting, like changing the dimmer switch in a room so slowly that no one notices the shift until the temperature of the entire space feels different. Around 2.6 million years ago, at the dawn of the Pleistocene, these orbital variations began generating more intense and more regular ice age cycles, marking the start of the Quaternary glaciations. Before this time, Earth experienced warm periods that lasted much longer and cold periods that were shorter and less extreme. But once eccentricity and the other orbital cycles aligned in a new climatic configuration, the pattern locked into a rhythm that eventually stabilized at the 100,000-year pulse seen today. One of the most remarkable discoveries in paleoclimatology is how scientists decoded these orbital patterns from the sediments on the ocean floor. As tiny marine organisms lived and died, their shells settled to the seabed, capturing chemical signatures that reflect the temperature of the water in which they grew. Oxygen isotopes in particular record the balance between ice stored on land and water stored in the ocean. Over millions of years, layers of sediment accumulated in a slow, steady rain of microfossils. And when researchers drilled into these deep-sea cores in the 1970s and 1980s, they found a rhythmic pattern in the isotopes, peaks and troughs matching cycles of glacial advance and retreat. When plotted against time, those cycles aligned perfectly with predicted variations in the Earth's orbit. It was a revelation. Nature had encoded its own astronomical logbook, scribbling the timing of each ice age directly into the floor of the world's oceans. This revelation also solved an old scientific puzzle about how such tiny orbital deviations could have such enormous climatic impacts. The answer lies not in the magnitude of the orbital shifts themselves, but in how they alter the distribution of sunlight across key regions and seasons, especially the mid to high latitudes of the northern hemisphere. Imagine summer days with sunlight just a little weaker than usual, cool enough that the winter snowpack doesn't melt entirely. Add that effect year after year, and what starts as a thin layer becomes a thicker crust, then a small patch of glacial ice, and eventually a vast frozen plateau. Orbital dynamics provide the whisper that starts the avalanche. As eccentricity shifts Earth's orbit over its long 100,000-year cycle, there are times when these northern summers become especially weak, aligning with low axial tilt or unfavorable precession angles that further reduce sunlight. These alignments don't happen often, but when they do, the climate system becomes vulnerable. It is in these windows that ice sheets gain their first footholds, tiny patches of unmelted snow forming the seeds of future leviathans. Once this process begins, the planet no longer needs continued orbital encouragement. Feedback loops begin reinforcing the cooling. Eccentricity has simply opened the door. To visualize this celestial choreography, imagine Earth as a dancer whose steps follow an ancient script written in gravity. The sun, the moon, and the giant planets tug gently at the dancer's path, stretching and bending it over time, while Earth itself pirouettes around its axis, wobbling slightly like a spinning top. The dance is slow, elegant, and utterly relentless, carving its influence not just on daily weather, but on the fate of entire epochs. No human living through a single lifetime would ever notice the change. Summers would seem as bright as always. But across 100 generations, the accumulating effects of this cosmic dance begin to alter the entire character of the planet. By the time the eccentricity cycle moves toward its most elongated phase, the background conditions for glaciation are set, though nothing dramatic has happened yet at ground level. Forests still grow, rivers still run, animals migrate, and the world feels on any given day, just as it always has. Yet the sky above is quietly adjusting the script of seasons, preparing the planet for the moment when sunlight will weaken just enough to let the first persistent snows survive. It is in this quiet preparation, subtle, invisible, but immense in consequence, that the seeds of every 100,000-year freeze are sown. And so, the stage is set, the orbit stretches, the seasonal timing shifts, and the northern summers grow slightly dimmer as centuries drift silently by. Nothing on Earth senses the danger yet, but the rhythm has begun. And soon, the next pieces of the mechanism, tilt, precession, and feedbacks, will join the motion, guiding the planet toward the first irreversible step into cold. Earth does not stand upright like a soldier on parade. Instead, it leans currently at an angle of about 23.5 degrees, and this tilt is the reason we have seasons at all. But the tilt is not fixed. Over a cycle of roughly 4,000 years, it shifts back and forth between about 22.1 degrees and 24.5 degrees, a small change that nonetheless reshapes the distribution of sunlight across the planet in profound ways. When the tilt is greater, seasons grow more extreme. Warmer summers, colder winters, and stronger contrast between the hemispheres. When the tilt weakens, seasons mellow, and it is this quiet mellowing, this gentle softening of summer warmth, that can allow snow to linger long enough for ice to take root. To understand the power hidden in this slight adjustment, imagine the northern hemisphere bathed in slightly less summer sunlight because the tilt is low. A cooler summer means that winter's snowpack, even if it wasn't exceptionally deep, may not fully melt. And if that snow remains unmelted, it forms a reflective blanket that bounces sunlight back into space, cooling the surface even more during the next year. If this pattern holds for centuries, a thin seasonal snowfield becomes a permanent patch of white, an embryo of a glacier that will thicken and spread. In the same way that orbital eccentricity acts as the timing mechanism, axial tilt provides the energy difference that determines whether ice sheets will grow or retreat. During periods of low obliquity, northern summers become too weak to erase winter's memory, and that is when the Earth becomes vulnerable to freezing. This tilt-driven vulnerability becomes especially potent when aligned with unfavorable orbital conditions. For example, if Earth is oriented such that the northern hemisphere's summer aligns with the farthest point from the Sun, aphelion, and if this occurs during a time of low tilt, the combined effect can significantly reduce summer warmth. It's a stacking of cosmic nudges, eccentricity setting the stage, precession adjusting the timing of the seasons, and tilt dimming the potency of summer. And when they align, the Earth slips into the conditions that allow ice to form and persist. Scientists often describe obliquity as the amplifier of orbital changes because it magnifies the climatic influence of the other cycles. A powerful summer can erase the threat of glaciation entirely, but a weak one can usher in tens of thousands of years of cold. Long before humans existed, this gradual shift in tilt was already sculpting the planet. Geological records show that prior to about 1 million years ago, the 41,000-year tilt cycle dominated Earth's ice ages. Ice would grow and shrink in rhythm with the obliquity, peaks, and troughs. Each time the tilt decreased, glaciers advanced. When the tilt increased, strong summers melted them back. But around 900,000 years ago, something changed. The planet cooled overall, carbon dioxide levels drifted lower, ocean heat content shifted, and the ice sheets began reacting differently. Instead of responding linearly to the tilt cycle, they began skipping cycles, growing larger and surviving longer. This marked the transition from the so-called 41,000-year world to the 100,000-year world, where eccentricity set the rhythm, but tilt still played a crucial shaping role. The key to this transition lies in understanding how ice sheets interact with tilt extremes. When the tilt is high, around 24.5 degrees, northern summers are powerful enough to melt even established ice sheets. But once the planet cooled and ice sheets grew thicker and more deeply rooted, it took stronger and stronger summers to erase them. Thus, many high-tilt phases were no longer enough to fully melt the ice, meaning glaciations could persist across multiple tilt cycles. Only when eccentricity and precession aligned with high tilt did the melting become intense enough to terminate a glacial period. This is why over the last 800,000 years, Earth's ice age rhythm shifted toward the longer pacing of the eccentricity cycle, even though tilt remained one of its most influential energy regulators. The sensitivity of high-latitude sunlight to tilt becomes clear when examining paleoclimate data. During low-tilt periods, northern summer sunlight can drop by nearly 15% compared to high-tilt peaks, a staggering reduction when spread across continents like North America and Eurasia. Imagine weaker sunlight falling over Canada and Siberia, sunlight that barely warms the soil, sunlight that fails to melt the last crust of snow from the previous winter. Year after year, that snow thickens. What begins as a slight seasonal anomaly becomes, over centuries, the scaffolding of an ice sheet extending hundreds of kilometers. Under low tilt, Earth tilts away not just physically but energetically, letting darkness seep further south. Because tilt governs the contrast between seasons, its long rhythm also shapes entire biomes. When tilt decreases, winters become milder, summers cooler, and vegetation shifts in response. Forests retreat, tundra expands, and species migrate following the edges of their preferred climates. In those ancient times, before Homo sapiens walked the savannas, these shifts influenced the evolution and dispersal of early hominins, shaping where they could live, what food sources they could exploit, and how environments changed around them over tens of thousands of years. Even then, the beat of obliquity quietly directed the flow of life. But the real climatic drama emerges when tilt interacts with the reflective power of ice. Suppose tilt remains low for several thousand years. Snow piles up, ice grows, reflectivity increases, and global temperatures begin to fall. Cooler temperatures reduce evaporation, weakening rainfall and encouraging drier conditions across continents, which in turn promotes dust storms that darken parts of the sky and cool the atmosphere further. All of this originates from a change of only a few degrees in Earth's tilt, a reminder of how delicate the climate system is and how deeply intertwined its components are. The gradual wobble of Earth's axis also has another profound effect. It changes which hemisphere experiences stronger seasonal contrasts. Although obliquity itself is symmetric, meaning both hemispheres are affected similarly, its combined effect with precession means one hemisphere can undergo particularly weak summers for thousands of years. And because the northern hemisphere contains the continents where major ice sheets can form, this symmetry becomes broken in practice. A slight change in tilt that reduces Arctic summer sunlight can create glaciers, whereas the same change in the southern hemisphere might only alter wind patterns or shift ocean currents. Thus, tilt acts not only as a global climate modulator, but also as a trigger for northern ice expansion. The records from Antarctic ice cores reveal the unmistakable imprint of tilt. Temperature peaks and troughs line up neatly with obliquity cycles, even in the deepest glaciations. Carbon dioxide rises and falls in tandem, following the pace set by tilt-driven temperature changes. From these records, we see that while eccentricity may govern the overall rhythm, obliquity provides the climactic pulse, beating steadily every 41,000 years, shaping Earth's climate with a whisper rather than a shout. As this section closes, the Earth's tilt stands poised at a place in its cycle that dims northern summers just enough to allow the first hints of persistent snow. The world feels unchanged on the surface. Trees sway quietly, winds move lazily across plains, and the seasons rotate as they always have. But somewhere in the slow machinery of the heavens, the planet leans a little differently, and this tiny lean will soon become one of the central threads of the ice age that follows. You can picture Earth as a spinning top, rotating confidently but also gently wobbling, its axis tracing a slow circle in the sky every 23,000 years or so. This means that the direction Earth's axis points toward the heavens is always changing. Today it tilts toward Polaris, the North Star, but long ago it pointed toward Vega, and in the distant future it will point somewhere else entirely. This change in orientation doesn't alter the length of a season or the tilt itself, but it completely transforms when each hemisphere receives its strongest sunlight, and this subtle timing shift is one of the hidden levers that pushes Earth toward ice or warmth. Precession matters because Earth's orbit is not perfectly circular. When the orbit is somewhat elliptical, the difference between being at perihelion, closest to the Sun, and at aphelion, farthest from it, becomes meaningful. Right now, Earth reaches perihelion in early January, giving the southern hemisphere slightly warmer summers and milder winters, while the northern hemisphere has cooler summers and harsher winters. But over thousands of years, precession slowly reverses this alignment, meaning that eventually northern summers will occur when Earth is closest to the Sun, making them hotter while southern summers cool. This slow shifting of the seasonal calendar around the orbit influences whether snow can disappear each year from northern lands, and that seemingly quiet influence has enormous consequences. When northern summers become weak because they coincide with aphelion, snow persists more easily. When they align with perihelion, the same region receives a boost of summer energy that melts ice quickly. The power of precession emerges most clearly during periods of high eccentricity when Earth's orbital shape is more elongated. In those times, the energy difference between perihelion and aphelion can reach nearly a 7% difference in incoming sunlight. It may not sound like much, but for the delicate margins that decide whether a patch of snow melts or endures, this slight change can determine the fate of an entire glaciation. In a world already predisposed to cooling due to a dim tilt or reduced greenhouse gases, a precession cycle that stacks weak summers atop a stretched orbit can tip the balance toward the beginning of an ice age. Conversely, when precession aligns northern summers with perihelion, even a thick, well-established ice sheet can begin to retreat under the renewed strength of summer heat. The impact of precession becomes especially mesmerizing when you follow it across time. For example, about 11,000 years ago, when the current interglacial was beginning, northern summers were aligned with perihelion, making them intense and helping melt back the remaining glacial ice. But this alignment drifts every millennium. By roughly 9,000 years from now, northern summers will occur near aphelion, making them slightly cooler, although not enough on their own to trigger a new ice age because current greenhouse gas levels are unusually high. Still, this slow drift is part of the long-term rhythm that has framed every glacial advance over the last million years. The precessional cycle also leaves unmistakable fingerprints in ancient climate records. In sediment layers taken from the deep ocean, tiny shells of once living organisms record the isotopic signature of the water they grew in, and these signatures trace rhythmic temperature shifts tied closely to the timing of precession. In African lake sediments, precession governs rainfall patterns by shifting the seasonal intensity of monsoons, creating alternating layers of lush vegetation and desert dust. Precession even influenced early human ancestors. During periods when precession strengthened African monsoons, lakes expanded across East Africa, supporting richer ecosystems that nurtured hominin evolution. During weak phases, aridity increased, driving migrations into new regions. This means the slow wobble of Earth's axis indirectly shaped where our ancestors stood, wandered, and survived. Yet the most dramatic influence of precession remains the way it modulates northern summer energy, and, through that modulation, influences the creation or destruction of ice. Even a slight shift in the timing of sunlight can mean the difference between snow lingering into the next winter or disappearing during a brief warm spell. A single year of lingering snow does little, but 10,000 such years, nudged consistently by precessional alignment, can create the foundation for glaciers that will eventually tower over landscapes. Once snow begins to accumulate, the world responds in subtle cascading ways. A reflective blanket of white bounces sunlight away, cooling the surface further. Cooler temperatures encourage tundra vegetation instead of forests, and this shift in plant life changes how much sunlight the land absorbs. Wetter snow compacts differently, altering the rate at which ice thickens. Winds strengthen as temperature gradients sharpen. Oceans adjust their thermal layers in response to slightly altered seasons. All of these effects begin with the faint shift in light caused by precession's turning of the axis. And this is why climate scientists call precession one of the key pacing mechanisms for glacial cycles. Precession also shapes the contrast between monsoon strength in each hemisphere. When the northern hemisphere receives stronger summer sunlight, the land heats more intensely, drawing in moist ocean air and amplifying monsoons from West Africa to South Asia. Precession-driven monsoon shifts leave visible marks in the Earth's geological record, alternating bands of clay and sand in desert regions, pollen layers revealing shifting ecosystems, cave formations known as speleothems, whose growth rates reflect ancient rainfall patterns. These records show that even in periods when ice sheets did not grow significantly, precession still sculpted the hydrological engine of continents, deciding where rivers flowed, where grasslands thrived, and where deserts crept forward. But the full climatic influence of precession unfolds only when combined with the other orbital cycles. Precession affects timing, obliquity affects strength, and eccentricity affects the background contrast between seasons. The three cycles weave together like threads in a cosmic braid, sometimes aligning to produce intense cooling, other times aligning to generate powerful warming, and often drifting halfway out of sync so the climate shifts gently rather than dramatically. But during those rare alignments, when eccentricity is high, tilt is low, and precession places northern summers at aphelion, the world becomes primed for glaciation. These alignments are infrequent, yet when they occur, the northern hemisphere begins to lose its ability to melt the previous winter's snow, allowing the first tiny steps toward continental ice to begin. As the planet continues its slow wobble through space, the orientation of the axis shifts one celestial notch at a time. Days pass, seasons flow, centuries drift by unnoticed, and nothing on Earth reveals the cosmic machinery at work above. But deep within that machinery, the timing of sunlight continues to slide, setting up the world for the next stage, when unmelted snow will harden, thicken, and quietly begin to alter the face of entire continents. The story now narrows to a single critical idea, an idea so deceptively simple that it took scientists more than a century to recognize its central role. The amount of summer sunlight falling on the far northern latitudes determines whether an ice age begins or ends. Not winter snowfall, not global temperatures, not the coldest part of the year. What matters most is whether summer in the region between 60° and 65° north, roughly the latitude of southern Alaska, central Canada, and the northern fringes of Europe, is strong enough to melt the previous winter's snow. If it isn't, that unmelted snow becomes the nucleus of future ice sheets. It is strange that a planetary freeze begins with a cool summer rather than a brutal winter, but this, as the paleoclimate records show, is the quiet hinge on which the world swings between warmth and deep glaciation every 100,000 years. To understand why this region is so crucial, imagine the planet several 100,000 years ago. The Arctic is largely ocean, but to the south sits an immense band of land where snow can accumulate. Canada, Alaska, Scandinavia, Siberia. Snow that lands on the ocean eventually melts or drifts away. Snow that lands on land can stay. And if summer sunlight weakens because of unfavorable orbital alignments, low tilt, precession placing northern summer near aphelion, and a stretched orbit amplifying the seasonal contrast, that snow does not melt completely. The next winter adds more. After a few centuries, the surviving snow compresses under its own weight, turning into firn, then into glacial ice. From that point onward, a feedback begins that is almost impossible to stop. Scientists studying ice cores from Greenland discovered that even tiny reductions in high-latitude summer sunlight, on the order of 20 watts per square meter during the weakest cycles, were enough to make the difference between complete melt and partial survival. Over dozens of summers, these slight reductions accumulate like quiet savings in a long-term account. Eventually, what looks like normal seasonal snow becomes a permanent layer of white armor. And because ice reflects far more sunlight than bare soil or forest, the surface cools even more, making the next summer even weaker relative to the previous one. This is how glaciers, once seeded, grow almost independently of the orbital conditions that first created them. The evidence for the dominance of northern summer sunlight appears in nearly every climate archive, in sediment layers showing dust from expanding tundra, in pollen records revealing shrinking forests, in the chemistry of ancient waters showing temperature shifts that match the rhythm of summer insolation changes. During periods when northern summers were strong, particularly at times when precession aligned them with perihelion, ice retreated. When summers weakened, especially when tilt was low, ice advanced. There are small variations, regional complexities, and exceptions influenced by ocean currents, but the broad pattern is unmistakable. The Arctic summer is the switch that turns ice ages on and off. This summer-sensitive mechanism also explains why ice ages occur primarily in the northern hemisphere, even though the southern hemisphere receives the same total amount of annual sunlight. The difference is geography. Antarctica is already glaciated and isolated by ocean currents, and large landmasses capable of sustaining glacial growth exist mainly in the north. The northern hemisphere's vulnerability is further amplified by the positioning of ocean currents and the distribution of heat between the hemispheres. If summers weaken slightly in the north, ice can form on land. If summers weaken in the south, the ice mostly forms over ocean or remains confined to Antarctica, which does not trigger global cooling nearly as effectively. Imagine, then, those vast northern lands under skies dimmed imperceptibly by orbital geometry. A summer arrives that is just a bit cooler than the one before. Snow lingers in small, sheltered valleys. A century later, the valleys are filled with hardened snow that never melts. A few centuries more, and these patches begin to connect, forming ribbons of white. As the ice expands, forests retreat southward, exposing more bare ground that changes reflectivity, wind patterns shift, and temperature gradients sharpen. The Arctic becomes a factory of cold, exporting frigid air masses into mid-latitudes, allowing winter storms to drop even more snow on the growing ice. What makes this process captivating is how long it takes, slow by human standards, but rapid compared to deep geological time. Within 10,000 years, a small region of persistent snow can seed an ice sheet many hundreds of meters thick. Within 20,000 to 30,000 years, that ice can extend thousands of kilometers, covering much of Canada and northern Europe under domes of ice taller than mountain ranges. Through all of this, the engine begins not with winter coldness, but with the muted warmth of northern summers. The cooling effect is further amplified by how the planet redistributes heat in response to declining summer insolation. As ice grows, the jet stream shifts southward, storm tracks migrate, oceans cool and begin storing more carbon dioxide, reducing greenhouse warming. Each of these changes begins with that first fragile step, snow that does not melt. And so the far north becomes the battleground on which summer sunlight fights to keep Earth warm. Climate scientists often point to a remarkable statistic. The difference between a world like today and a world buried under massive ice sheets is governed by only a few % change in regional summer sunlight. A small shift barely noticeable in the day-to-day experience of ancient humans can produce the difference between global warmth and a frozen world. This sensitivity reveals both the power and fragility of Earth's climate system. The importance of far northern summers also helps explain why the last few 100,000 years of Earth's history look the way they do. During some orbital alignments, summers grew strong enough to obliterate ice sheets in dramatic, rapid pulses of melting-ending glacial periods. During other alignments, summers weakened and ice began creeping forward again. These cycles created the familiar sawtooth pattern seen in climate records: slow glacial growth, rapid termination, slow re-establishment, rapid melting. Each growth phase began with quiet summers. Each termination began with suddenly fierce ones. This principle also shapes the interglacial we live in now. The Holocene began about 11,700 years ago, when northern summer sunlight was unusually strong due to precession aligning summer with perihelion. Since then, that sunlight has been slowly weakening. Without modern human influences, the Earth would likely begin drifting gradually toward another glacial period in several thousand years, though not imminently. Today, however, elevated greenhouse gas levels have dramatically altered that natural trajectory, essentially overpowering the gentle dimming of northern summers and pausing the natural pace of glaciation. Still, the underlying mechanism remains in place. As long as Earth continues its orbital cycles, the strength of northern summer sunlight will remain the quiet metronome of the glacial beat. In the deep rhythm of Earth's past, present, and future, this narrow latitudinal band remains the hinge upon which the world's climates swing. And now, with summer insolation decreasing but global temperatures rising, the planet finds itself in a rare moment where ancient rhythms and modern forces briefly collide. Yet, in the narrative we follow, we step back into that older world, the world before human influence, where the summer sun over northern lands slowly dims and the first thin layers of unmelted snow mark the beginning of the great ice sheets whose birth will soon change the face of continents. You can imagine a landscape in the far northern latitudes, perhaps somewhere in what is now central Canada or the high plateaus of Scandinavia, where the summers have grown just cool enough that winter's snow no longer fully disappears. At first, it is only a patch of stubborn whiteness clinging to the shaded side of a ridge. But this small persistence is the seed of a transformation that will take millennia to reveal its full power. The process begins with something simple: snowfall that survives summer. The first few years offer no hint that anything unusual is happening. Snow lingers a little longer each year, but it still seems temporary. Yet as centuries pass under the influence of weakened northern summers, each year adds a thin new layer of snow atop the old. The lower layers compress under the weight of the fresh snowfall. Air is slowly squeezed out, crystal boundaries rearrange, and the fluffy snow gradually becomes firn, a dense, grainy intermediate form. With enough compression, usually across a few tens of meters of overlying snow, firn transforms into glacial ice, a kind of frozen stone that flows under its own weight. Once this transformation begins, an entirely new behavior enters the system. Ice starts to move. This movement is almost imperceptible at first. Ice behaves rigidly on short timescales, but flows like cold honey over centuries. In the earliest stages, this flow only affects areas a few meters thick, but as the accumulation continues, the patches of permanent snow creep slowly downhill, merging with neighboring patches. Ridges and valleys that once retained distinct microclimates begin to blur under sheets of growing white. The landscape takes on curves imposed not by bedrock, but by frozen mass, domes, lobes, and spreading tongues of ice that advance quietly outward from their birthplaces. As the ice spreads, the land beneath responds. Forests retreat, unable to take root in soils that remain frozen year-round. Tundra grasses push southward, replacing woodlands with hardy shrubs and mosses. Rivers shift course when ice blocks their valleys. Small lakes freeze over for longer periods, eventually becoming buried entirely. Animals move with the shifting climate zones. Caribou, musk oxen, and the ancestors of mammoths retreat toward regions still suitable for feeding. Predators follow. Ecosystems rearrange themselves in slow waves across thousands of kilometers. In these early phases, the ice sheet is still vulnerable. A strong shift in orbital alignment could melt it back, and the climate still hovers in a delicate balance. But as long as summers remain weak and winters continue delivering snow, the ice expands. Scientists studying landforms carved by ancient glaciers have reconstructed this early growth from clues left behind. Erratic boulders transported hundreds of kilometers, scratched bedrock surfaces called striations, and deposits of unsorted sediments known as till. These features show that once ice begins to move, it becomes a powerful sculptor, grinding mountains, deepening valleys, and carving basins that will later fill with lakes. The growth of the Laurentide ice sheet in North America and the Fennoscandian ice sheet in Europe followed exactly this pattern. At their maximum extents, these ice sheets were astonishing in size. The Laurentide stretched across modern Canada and parts of the northern United States, covering an area nearly as large as the entire Antarctic ice sheet today. At its thickest, near Hudson Bay, it rose more than 3 kilometers above sea level, taller than many mountain ranges. These massive structures began as nothing more than persistent snowfields that refused to melt, proving that the birth of glacial giants is rooted in the quiet resilience of tiny patches of snow. The early formation of ice sheets also created subtle but important changes in Earth's climate machinery. For instance, as the ice expanded, it altered atmospheric circulation. Cold air masses grew larger and more stable, pushing the jet stream farther south. Storm tracks shifted, delivering more snowfall to regions already primed for glacial growth. A reinforcing loop formed. More snow created more ice, which redirected winds, which brought more snow. This loop is one of the reasons glaciation accelerates once it begins. It's not simply that the ice grows, it creates the conditions for even faster growth. Beneath the ice, the landscape groaned and reshaped. The weight of a growing ice sheet depresses the Earth's crust through a process called isostatic sinking. Under kilometers of ice, the crust can drop by hundreds of meters, creating broad basins. When the ice eventually melts thousands of years later, these basins rebound slowly, rising like a mattress released from pressure. Evidence of this rebounding continues today. Parts of Scandinavia and Canada are still rising several millimeters per year as they recover from the ice loads of the last glaciation. But during the initial growth phase, the sinking accentuates the conditions that allow more ice to accumulate, lowering the land further into cooler atmospheric layers where snow and ice thrive. The first ice sheets formed unevenly. Some regions accumulated ice rapidly due to constant snowfall, while others grew more slowly. But what matters in the long arc of glaciation is persistence, not speed. As decades blend into centuries and centuries into millennia, the small patches of ice become regional features and then continental ones. The reflective surface of the ice increases Earth's overall albedo, meaning more sunlight is reflected away from the planet. This reduces global temperatures by a small but meaningful amount. Cooler oceans begin absorbing more carbon dioxide, lowering greenhouse gas levels and amplifying the cooling, another feedback loop supporting the ice's growth. At this stage, the ice sheets no longer respond linearly to orbital changes. When summers weaken further due to ongoing changes in precession or tilt, the ice grows faster. When summers strengthen slightly, the ice might stabilize but not retreat significantly. This gives glaciers a kind of memory, allowing them to persist even when the immediate climate conditions weaken. By now, the beginnings of the ice sheets are locked in, sustained by their own feedbacks and by the layers of accumulated snow that act like long-term climate savings. Even the sea responds. As water becomes trapped in growing ice sheets, global sea levels begin to fall. In the early stages of glaciation, the sea may drop by only a few meters, but over thousands of years, the drop becomes dramatic, eventually exceeding 120 meters at full glacial maximums. Coastlines extend outward, exposing continental shelves that have been submerged for ages. Land bridges appear, most famously the one between Siberia and Alaska, allowing animals and eventually humans to migrate into new territories. These migrations, too, trace their origins to those first fragile years when snow simply refused to melt. As this section draws to its close, the scene is set. Ice sheets have begun their long, slow march across northern continents. The world has dimmed slightly under weakened summers, and the feedbacks necessary for a glacial period have awakened. Nothing dramatic happens in any single year. No ancient human would have noticed the beginning of this transformation. Yet the small, persistent survival of snow across a few summers has begun a process that will reshape the planet for tens of thousands of years. As the ice sheets continue their slow expansion across the northern continents, another force awakens, an invisible partner to the spreading white world, and it becomes one of the most powerful amplifiers in the entire glacial machine. This force is albedo feedback, the process by which snow and ice reflect sunlight back into space, cooling the planet further and encouraging even more ice to form. At first, it seems gentle, almost delicate, a thin sheet of white reflecting slightly more summer sunlight than the dark soil or forest beneath it. But as ice spreads, reflectivity compounds, and Earth begins to tip into a self-reinforcing spiral of cooling. This is the quiet engine behind the deep freezes that occur every 100,000 years, the mechanism that takes a small orbital nudge and transforms it into a planetary transformation. To appreciate how powerful this feedback is, imagine a summer day in the early stages of glaciation. A valley that once absorbed sunlight through dark tundra vegetation now glistens with bright snow. Where the land once captured warmth, it now reflects as much as 80% of incoming sunlight back into space. The surrounding area is still warm as usual, but this one glacial seed does not. Over the next few centuries, similar patches appear across increasing parts of the northern continents. Forests give way to tundra. Tundra gives way to persistent snowfields. Snowfields give way to ice. The overall reflectivity of Earth increases, and global temperatures drop by fractions of a degree. Fractions that may sound trivial, but become decisive at the margins where snow meets sunlight. The growth of reflectivity across northern landscapes expands in waves. First, snow lingers in lower elevations. Then, high plateaus acquire year-round frost. With each new surface that turns from dark to light, the planet's energy budget shifts. Less sunlight absorbed means less heat stored. Less heat stored means cooler summers. Cooler summers mean more snow survives, and so the loop closes on itself, tightening with each pass. Climate scientists often illustrate this process with simple models, and even in the simplest scenario, just a patch of reflective ice next to a darker surface, the resulting cooling effect cascades. Multiply that by millions of square kilometers, and the magnitude becomes astonishing. A single percentage point increase in global reflectivity can cool the entire planet by 1 degree Celsius or more over long timescales. This feedback is not merely theoretical. Its fingerprints appear in the geological record. Sediments from glacial periods contain higher concentrations of certain isotopes, indicating colder ocean temperatures, which align precisely with periods of increased surface reflectivity. Pollen records show forests retracting thousands of kilometers southward, confirming that areas once rich with vegetation had turned into white plains of snow and ice. Ice cores from Antarctica show a drop in greenhouse gases, particularly carbon dioxide, which declines as the planet cools, a secondary feedback that strengthens the chill. The Earth becomes not simply colder, but more reflective, drier, windier, and less able to shed the cold that gathers in its northern heart. One of the most mesmerizing consequences of growing ice sheets is their ability to alter the trajectory of sunlight across the atmosphere. When ice expands, it cools the air directly above it. Cold air is dense and heavy, so massive domes of frigid atmosphere build over the ice sheets, pushing surrounding air masses outward. This shift influences storm tracks, often redirecting them toward regions already primed for snowfall. Over North America, for example, the Laurentide ice sheet created a cold air dome that nudged the jet stream south, guiding moisture-rich storms from the Pacific and Atlantic into areas where temperatures were too low for melting. The storms dropped snow, not rain. The snow lingered. The ice thickened. In Europe, a similar pattern unfolded where the Fennoscandian ice sheet shaped the behavior of North Atlantic winds and storm systems. The reflective power of ice further enhances these atmospheric rearrangements. Sunlight bouncing off ice does not heat the surface, which means air remains cooler and more stable above glaciated regions. This encourages inversion layers, zones where cold air becomes trapped near the surface under slightly warmer air aloft, strengthening the persistence of cold. The more stable the air, the less mixing occurs. The less mixing, the colder the surface remains. This atmospheric stagnation becomes another feedback that reinforces glaciation. But albedo feedback does not work only on land. Sea ice also expands as the climate cools, forming floating white shields across Arctic waters. Sea ice reduces the exchange of heat between the ocean and atmosphere, which means the ocean retains more of its cold, deep water while the air above grows even cooler. During glacial periods, sea ice extended far beyond its modern boundaries, reaching farther into the North Atlantic and sometimes forming seasonal coverage in areas that now remain ice-free year-round. The spread of sea ice strengthens global cooling even further. When sunlight strikes open ocean, the dark surface absorbs most of it, heating the water. When sunlight strikes sea ice, most energy is reflected instead. This is the same principle that amplifies land ice, but because the Arctic Ocean covers millions of square kilometers, its participation in the glacial feedback loop is enormous. Another critical element in this feedback chain is the way expanding ice alters the hydrological cycle. As temperatures cool, evaporation weakens. Less evaporation means fewer atmospheric water molecules, which is particularly impactful because water vapor is a potent greenhouse gas. With lower humidity, the greenhouse effect weakens, promoting yet more cooling. Snowfall continues, but overall precipitation decreases, meaning that while the world becomes snowy in some areas, it becomes drier in many others. This dry atmosphere allows heat to escape more easily into space, especially at night, reinforcing the trend toward glacial expansion. With each kilometer of new ice that spreads outward, the world's climate system shifts further from the warm equilibrium of interglacial periods. The contrast between dark patches of open land and bright stretches of snow becomes sharper, guiding winds into new patterns. Dust storms increase over deserts as the planet dries and vegetation retreats. That dust, carried across continents, sometimes settles on ice sheets themselves, darkening patches of snow and briefly slowing the albedo feedback. But the effect is limited. Snow eventually buries the dust, restoring the reflective surface. Long-term, the feedback remains overwhelmingly positive. More ice encourages more cooling. Paleoclimate simulations reveal that without albedo feedback, Earth's glacial cycles would be far less dramatic. Orbital changes alone could cool the planet modestly, but not enough to produce ice sheets kilometers thick. It is the amplification through albedo that transforms a gentle astronomical rhythm into the dominant sculptor of landscapes. Albedo, in this sense, acts as the climate system's magnifying lens, taking the faint whisper of weakened summer sunlight and turning it into a shout that echoes across millennia. Yet, even as albedo feedback grows powerful, it does not act alone. Ice sheets demand reinforcement from other feedback loops, including cooling oceans and changing carbon dioxide levels, mechanisms that will join the story soon. But for now, reflectivity reigns as the first great amplifier, the force that gives glaciers their relentless momentum and sets Earth firmly on the path toward full glaciation. As this section draws to a soft close, the world glimmers with spreading whiteness beneath weakened summer skies. The reflectivity of ice has begun to reshape the energy balance of the entire planet, guiding the climate toward colder and colder conditions. The snow that once lingered in quiet valleys has now become vast, shimmering fields stretching beyond the horizon, fields that promise only one direction for Earth to travel, deeper into its 100,000-year freeze. While the ice sheets grow across Canada and northern Europe, the oceans begin their own transformation. And this slow but persistent shift in carbon storage becomes one of the most powerful and underrated forces that push Earth further into an ice age. Through a combination of cooling temperatures, changing circulation, and altered biological activity, the oceans start to breathe in more CO2 than they release. And with each inhalation, the atmosphere loses a bit more of its insulating blanket. To understand why this happens, imagine the ocean as a vast layered world of cold depths and warmer surface waters. Cold water can hold more dissolved gases than warm water, including carbon dioxide. As the planet cools due to orbital changes and growing ice, the surface of the ocean cools as well, allowing it to take up more CO2 from the atmosphere. Each molecule of carbon dioxide that dissolves into seawater reduces the greenhouse effect just slightly, letting more heat radiate out into space. The cooling deepens, more CO2 is absorbed. And so a new feedback loop begins, one that drags Earth further into its long winter. This phenomenon is not theoretical. Ice core records from Antarctica, stretching back over 800,000 years, show that carbon dioxide levels drop dramatically during glacial periods, often falling to around 180 through 200 parts per million, compared to about 280 ppm during warmer interglacials. These reductions are not small fluctuations. They represent a major weakening of Earth's natural greenhouse insulation. And the pattern matches perfectly with ocean changes. Whenever the planet cooled and ice expanded, CO2 fell. Whenever the planet warmed and ice retreated, CO2 rose again. The oceans played the central role in these swings. As the surface waters cool, they become denser and sink, carrying dissolved CO2 with them into the deep ocean. In glacial climates, deep ocean circulation patterns change, often becoming more stratified. The cold, dense water near the poles plunges downward, forming what are called deep water masses, which store carbon for centuries or even millennia before it resurfaces. During glacial periods, the deep ocean holds significantly more carbon than it does during warm interglacials. This sequestration happens slowly, silently, and in massive quantities. The atmospheric CO2 drawdown that results then amplifies global cooling. But that is only part of the story. Glacial oceans are not simply colder, they are less ventilated. The circulation that normally brings deep waters back to the surface slows down in some regions because surface waters freeze into sea ice or become so cold and fresh that they form insulating layers above the deeper, saltier water. With less upwelling, less CO2 escapes back into the atmosphere. It's as if the ocean has closed many of the vents through which it normally exhales carbon. The deep waters become a vast storage chamber for CO2, held there by sluggish circulation and cold temperatures. Biology also plays a surprising role. During glacial periods, increased dust from expanding deserts lands on the ocean's surface. This dust contains iron, a crucial nutrient for marine phytoplankton. In iron-limited regions such as the Southern Ocean, extra iron from dust boosts productivity, meaning more phytoplankton grow and absorb CO2 during photosynthesis. When these organisms die, some of their carbon-rich remains sink into the deep ocean, locking away carbon for long periods. This phenomenon, known as the iron fertilization effect, further lowers atmospheric CO2 levels and enhances cooling. These combined processes, physical, chemical, and biological, turn the oceans into a massive carbon sink during glacial expansion. Their CO2 uptake strengthens the cooling that the ice sheets and orbital changes have already begun. It is another positive feedback loop. Cooling oceans absorb more CO2, which causes more cooling, which allows more CO2 absorption, and so on. This is why atmospheric CO2 levels fall so reliably during each ice age in the last million years. The visibility of this process becomes clear when looking at the timeline of past glaciations. Each time northern summer sunlight weakens and ice sheets begin to grow, CO2 levels begin to drop shortly afterward. And once CO2 declines, the pace of glaciation increases. Ice sheets thicken more rapidly, albedo increases, global temperatures fall more sharply. Without this CO2 feedback, Earth's ice ages would be far milder, perhaps small regional glaciations rather than continental-scale freezes. Instead, the oceans turn a modest orbital cooling into a global transformation. Another fascinating aspect of glacial ocean behavior is the way sea level interacts with it. As ice sheets grow, sea levels fall, eventually dropping more than 120 meters at full glaciation. When this happens, shallow continental shelves become exposed to the air. Rivers extend farther out, coastal ecosystems shift. But deeper still, the fall in sea level increases the salinity of remaining ocean water, because the total volume of water decreases while the amount of dissolved salt remains the same. Saltier water is denser, which can further alter ocean circulation patterns, encouraging more storage of cold, dense, carbon-rich water in the deep. All these changes mean that during glacial periods, the ocean becomes a place of pronounced vertical differences. The surface grows fresher and colder, often capped by seasonal or even perennial sea ice. Beneath lies a vast reservoir of older, carbon-rich water that remains so isolated that it rarely rises to the surface. This isolation is one reason why glacial oceans trapped so much CO2. They simply did not mix enough to release their stored gases. The stability of the deep ocean's carbon reservoir during glacial times also explains why glacial climates were so persistent. Even if orbital conditions shifted slightly toward warming, the ocean's CO2 storage would delay any substantial greenhouse increase until circulation patterns changed, usually thousands of years later. This made glacial climate slow to retreat, giving ice sheets long lifespans even when the astronomical forcing began to reverse. Yet, in this phase of the story, the oceans are not fully responsible for the cooling. They are simply amplifying and reinforcing the direction that orbital changes and ice growth have already initiated. The glacial world is still forming, not yet reaching its greatest extent, and the ocean's deepening carbon drawdown is the second major feedback loop after albedo. Soon, the climate system will experience even broader rearrangements, winds shifting, atmospheric patterns transforming, dust thickening in the skies. But for now, the oceans continue their silent inhalation, drawing down the greenhouse gases that once helped keep Earth warm. As the section closes, imagine the world from a vantage point above the oceans. The surface gleams with patches of expanding sea ice. Cold, dense currents plunge downward along the coasts of Greenland and Antarctica. The deep ocean begins storing carbon that will not see the atmosphere again for millennia. Above it all, the atmosphere grows clearer, drier, less insulated. The world cools quietly, steadily, and irresistibly, pulled along by the breath of the oceans as they help usher Earth deeper into its 100,000-year freeze. As the ice sheets sprawl across continents and the oceans draw down carbon dioxide, another transformation begins to shape the planet, one that unfolds not through ice or atmosphere alone, but through the immense, slow, and powerful motions of the oceans themselves. Beneath the surface, deep currents shift, Overturning cells weaken or reroute, and heat that once flowed freely between hemispheres becomes trapped or diverted. This silent reordering of the world's oceans becomes the third great feedback in Earth's glacial machinery, tightening the planet's march toward full ice age conditions. It is here, in the dark and frigid depths of the sea, that one of the most dramatic but least visible climate reorganizations unfolds. To understand how such underwater changes can reshape the entire planet, imagine the ocean as a global conveyor belt, a continuous loop of warm surface water and cold deep water that circulates through every major basin. Today, the Atlantic Meridional Overturning Circulation, or AMOC, pulls warm water northward toward Europe, where it cools, sinks, and flows back south in deep currents. This system transports massive amounts of heat, moderating climate patterns across vast regions. But during glacial periods, as ice expands and global temperatures drop, this conveyor belt slows, redirects, or even temporarily shuts down. The slowing is not sudden. Instead, it unfolds over thousands of years as surface waters cool, sea ice spreads, and fresh water from accumulating snow alters ocean density. Freshwater plays a central role because it disrupts the very process that drives deep water formation. Cold water is dense and sinks, but cold freshwater is less dense than cold salty water. As glaciers expand, they trap enormous amounts of fresh water, locking it into ice and lowering sea levels. The ocean becomes saltier overall, but surface waters near growing ice sheets often become fresher due to increased snowfall and expanded sea ice that freezes and melts seasonally. In regions like the North Atlantic, where sinking surface water drives the deep return flow, this freshening can slow the descent of water into the abyss. And once that descent weakens, heat transport falters. This change ripples across the globe. When less warm water reaches the high northern latitudes, those regions cool more quickly. When deep water formed during glacial times flows southward, it spreads carbon-rich water through the deep oceans, locking away heat and greenhouse gases. The southern hemisphere responds as well. Antarctica, isolated by the circumpolar current, becomes even more thermally isolated. Winds intensify around the Southern Ocean as temperature gradients sharpen. And with stronger winds, deep waters rich in carbon dioxide are sometimes stirred upward, but often they remain trapped below cold layers of surface water. The whole system becomes stratified, cold, fresh layers above, colder, saltier layers below, and sluggish mixing between them. This stratification is one of the defining characteristics of glacial oceans. In warm periods, surface and deep waters mix more readily, allowing heat and nutrients to move through the ocean. But in glacial times, the sharp temperature and salinity contrasts prevent this mixing. The deep ocean becomes older in a chemical sense, its water remaining in place for longer periods, accumulating nutrients and carbon from decaying organic matter. Meanwhile, the surface becomes a colder, lighter layer that seals off the depths like a lid on a pot. This layering not only keeps CO2 trapped at depth, but also reduces the upwelling of warm water that might otherwise moderate the cooling climate. Scientists have traced these changes by analyzing the shells of tiny marine organisms preserved in deep-sea sediments. Isotopic signatures, particularly of carbon and oxygen, reveal how water masses shifted during glacial periods. They show that the deep Atlantic became dominated by water formed in the Southern Ocean during ice ages, replacing the vigorous northern deepwater formation seen in interglacials. This reversal in the deep circulation pattern profoundly changed heat distribution across the planet. The North Atlantic grew frigid, intensifying glacial conditions in Europe and North America, while the Southern Ocean became a sink for deep carbon-rich waters. One extraordinary outcome of this reordering is how it influenced the pace and intensity of glaciation. As circulation slowed, less heat traveled north to melt snow during summer. This made northern regions even more vulnerable to accumulation. Meanwhile, the deep storage of carbon dioxide kept greenhouse levels low, allowing global temperatures to drop further. In addition, a slower circulation meant that the deep ocean acted like a gigantic cold reservoir. Once the planet cooled enough, this deep cold stabilized the climate in a glacial state, making any return to warmth much more difficult without a strong orbital push. Another surprising consequence lies in the southern hemisphere. Even as the North froze, Antarctica sometimes experienced warmer intervals due to changes in how heat moved between the deep and surface waters around the South Pole. This seesaw pattern, called the bipolar seesaw, is evident in the ice core records. When the North Atlantic cooled rapidly due to circulation weakening, the Southern Ocean often warmed slightly as heat accumulated in the deep Atlantic and eventually moved southward. This warming never melted the Antarctic ice sheet entirely, but it altered sea ice extent, influenced winds, and affected the timing of CO2 release from the ocean, changes that further modulated the global climate. The reorganization of ocean currents also transformed ecosystems. In glacial times, nutrient-rich waters from the deep were sometimes trapped below the surface, reducing biological productivity in some basins. In others, intense winds drove upwelling, fertilizing the seas and stimulating bursts of phytoplankton growth. These biological shifts influenced how much carbon was locked away in organic material, adding yet another layer to the carbon feedback loop. Meanwhile, the Pacific Ocean responded differently. Its vast expanse and slower overturning rate meant that glacial cooling created enormous reservoirs of cold water that changed salinity patterns across entire basins. Currents like the Kuroshio and the California Current shifted positions, altering climate along the coasts of Asia and North America. The tropical Pacific, influenced by changes in trade winds and sea surface temperature gradients, experienced different El Niño-La Niña-like patterns from those seen today, affecting rainfall across large swaths of the planet. All of these oceanic rearrangements lead to a subtle but decisive tipping of the climate system. The world becomes not simply colder, but structurally different. Heat no longer moves the way it once did. The pipes of the global ocean circulation are partially rerouted or constricted, reducing the efficiency of Earth's thermal engine. Every shift favors greater cold in the long term. As this section concludes, imagine Earth from above, but now focus beneath the surface. Vast rivers of water, invisible to any eye, sweep slowly through the deep, carrying with them carbon, nutrients, and cold. The Northern Ocean grows stratified and sluggish. The Southern Ocean churns in fierce winds. The equatorial currents adjust, sending ripples of climate influence across continents. And through it all, the ocean continues its quiet but enormous role, redistributing heat, storing carbon, and shaping the world into the glacial giant it is becoming. By now, the world is firmly descending into its long glacial night, yet the transformation is far from complete. Even with ice sheets expanding, oceans storing carbon, and circulation patterns shifting into new configurations, another powerful ingredient arrives to reinforce the chill, one that sweeps across continents, settles on ice sheets, darkens skies, and subtly shapes the planet's cooling in ways both surprising and profound. This ingredient is dust. During glacial periods, Earth grows windier, drier, and dustier, and this dust becomes both a signal and a driver of deepening cold. The rise of dust, dryness, and strengthened winds forms the fourth major feedback in the glacial engine, adding another layer of acceleration to the freeze every 100,000 years. To understand why dust plays such an important role in glaciation, imagine a world that has already cooled substantially. As temperatures drop, the atmosphere holds less moisture. Rainfall declines, evaporation weakens, vegetation retreats across wide swaths of continents, particularly in mid-latitude regions adjacent to growing ice sheets. Grasses become sparse, soils loosen, and vast plains that were once anchored by roots begin to dry and crack. In this more arid world, the land becomes vulnerable to erosion by wind. Once stable soils are swept skyward in massive plumes of dust that travel thousands of kilometers before settling onto surfaces far from their origin. This dust activity is not a minor phenomenon. It is a global transformation. Ice cores from Antarctica contain layers of dust many times thicker during glacial periods than during warm interglacials. Some layers show dust concentrations up to 20 to 40 times higher than today, indicating a planet that had become profoundly wind-driven and dry. Marine sediment cores reveal similar patterns, vast deposits of wind-blown particles from Asia blanketing the North Pacific, Saharan dust traveling across the Atlantic in volumes far greater than modern measurements. Dust from Patagonia sweeping into the Southern Ocean. These dust layers record not only environmental conditions, but also mark turning points in glacial progression. What gives dust such climatic importance is the way it interacts with both sunlight and ice. Dust in the atmosphere can reflect incoming sunlight, cooling the surface below. At the same time, dust settling on ice sheets can darken their surface, making them absorb more sunlight, which, counterintuitively, can either slow an ice sheet's expansion or speed up melting in localized patches. But here is the subtle truth. During the early and middle stages of glaciation, the cooling effect of atmospheric dust greatly outweighs its darkening effect on ice. Dust high in the atmosphere scatters sunlight back into space, especially in regions where skies are otherwise clear and dry. This scattering cools land surfaces further, especially at mid-latitudes where dust storms are most intense. The effect is small year to year but enormous over millennia. Dust also plays an important role in regulating Earth's biological carbon cycle. These airborne particles carry iron, an essential micronutrient that many parts of the ocean lack. When dust falls into iron-poor regions, especially the Southern Ocean, it stimulates phytoplankton growth. This biological fertilization increases the ocean's uptake of carbon dioxide, further reducing atmospheric CO2 levels and reinforcing global cooling. This elegant connection means that dust driven by cooler and drier climates indirectly strengthens the very forces that create more dust, a looping, self-reinforcing dynamic. The rise of dust also reveals how climate zones shift dramatically during glaciation. As ice sheets push southward and temperatures fall, the band of strong westerly winds intensifies. These winds, flowing around the edges of the cold, dense air, masses above ice sheets, generate powerful storms that sweep across continental interiors. Over Eurasia, a vast zone known as the Loess Belt formed during glacial periods, built from layer upon layer of wind-blown silt. In places like the Chinese Loess Plateau, these deposits reach thicknesses of 200 meters, a towering archive of glacial winds and dust cycles spanning millions of years. Similar Loess deposits formed across Central Europe and the American Midwest, each layer marking centuries of strong winds and dry conditions. The dryness that fuels dust formation spreads beyond the continents. Subtropical regions experience weakened monsoons during glacial periods because cooler global temperatures reduce the thermal contrast between land and ocean, contrast that normally powers monsoon rainfall. With weaker monsoons comes less vegetation, more exposed soil, and more dust. The Sahara, for example, expands dramatically during glacial periods, becoming one of the largest dust sources on Earth. The Australian interior dries as well, producing dust that settles across the Southern Ocean. Everywhere, drought marches in lockstep with cooling. One of the most fascinating effects of dust lies in how it influences sea ice. As dust cools the atmosphere through scattering and reflection, Arctic and Antarctic waters freeze earlier in the season. Sea ice expands more easily into waters that have lost some of their summer warmth. This, in turn, strengthens albedo feedback, because sea ice is even more reflective than glacial ice. The expanding sea ice cools surrounding waters and modifies ocean atmosphere heat exchange, reinforcing the onset of full glacial conditions. Dust also affects high-altitude glaciers on mountain ranges. In places like the Himalayas, the Andes, and the Alps, dust deposited on glaciers sometimes accelerates melting by darkening the ice surface. But in a colder global climate, the dominant effect is the suppression of melt by reduced sunlight reaching the ground, caused by dust haze in the air. Glaciers in many mountain regions expand, contributing additional freshwater storage in ice and lowering sea levels further. These mountain glaciers become small but important contributors to the planet's overall glacial mass balance. The presence of dust also influences the timing of glacial maxima. Some climate models suggest that dust loading in the atmosphere can lower global temperatures by as much as 1 10^3 when dust levels are extremely high. This is enough to tip borderline regions into persistent snow cover. In fact, some scientists believe dust may have played a key role in pushing Earth toward the coldest phases of past ice ages, particularly when orbital forcing was not especially strong. Dust, then, becomes a silent amplifier. one that steps in to push the climate over thresholds established by the more fundamental astronomical cycles. Another intriguing aspect of dust feedback lies in how it interacts with cloud formation. Dust particles can act as cloud condensation nuclei, meaning they help clouds form more easily. During glacial periods, when dust is abundant, clouds may form more frequently or with different properties. Some clouds reflect sunlight effectively, while others trap heat, but during cold periods, the balance tends to favor reflectivity. This further shifts Earth's radiative balance toward cooling. In regions near ice sheets, dust thickens in dense layers on the landscape. These layers preserve the footprints of wind currents that shaped the world tens of thousands of years ago. Paleoclimatologists can read these layers like pages in a book, reconstructing year-by-year variations in wind strength, storm tracks, and glacial advance. The dust tells a story not just of climate change, but of shifting atmospheric circulation and continental desiccation. By the time dust storms reach their full strength, the world has crossed an important threshold. Ice continues growing, the oceans continue storing carbon, winds remain strong and dry. The glacial system is now fully engaged, and every major feedback is pointing in the same direction. Deeper cold. As this section closes with a gentle breath, imagine a world where winds howl across grassless plains, carrying clouds of dust that dim the sunlight before it touches the ground. Imagine deserts expanding, skies pale with suspended particles, and the distant gleam of ice sheets stretching southward under cool summer skies. The Earth is now gripped by forces that reinforce each other, all moving toward the same inevitable outcome, a planet wrapped in deepening ice. Life itself begins to reshape and respond to the cold, creating sweeping changes across continents. This is the era often described as a planet of giants and winds, a world where enormous mammals roam windswept steppes stretching from France to Siberia, where dust-laden gusts scream across thousands of kilometers, and where ecosystems reorganize in ways that define the character of Earth for tens of thousands of years. The ice sheets may be the architects of this frozen world, but the creatures and landscapes that fill its margins give the glacial Earth its soul. The expansion of ice sheets forces ecosystems to migrate. Forests are among the first to retreat. In Europe, birch and pine withdraw southward. In Asia, dense forests give way to open grasslands. North America sees its hardwood forests shrink dramatically as cold-adapted spruce and fir dominate the remaining forest belts. Where forests vanish, vast plains emerge, open, dry, and windy landscapes known as the Mammoth Steppe. This biome, stretching unbroken from Western Europe across Siberia, Alaska, and down into parts of North America, becomes the largest ecosystem of the late Pleistocene. It is unlike any habitat on Earth today, frigid yet productive, cold but rich with grasses, sedges, and herbaceous plants capable of supporting huge herbivores. And those herbivores thrive. Woolly mammoths dominate these steppes, their thick coats and curved tusks icons of the Ice Age world. They graze in herds that sometimes number in the hundreds, carving paths through snow and stirring up dust as they move across frozen ground. Alongside them roam woolly rhinoceroses, steppe bison, giant deer with antlers wider than a person is tall, musk oxen, and wild horses. Predators follow their trails. Cave lions the size of modern African lions, but built for the cold. Scimitar-toothed cats with long, curved canines built for slicing flesh. Dire wolves with powerful jaws. These animals form a living tapestry shaped by the harsher climate, the shifting vegetation, and the expanding ice. The winds that shape this steppe world are relentless. Driven by strong temperature differences between glacial ice and exposed plains, they roar across continents, carrying fine particles of silt and dust. The Mammoth Steppe is not just grassy, it is dusty, bathed in pale sunlight filtered by airborne loess. Standing there, one would feel constant wind, see horizons blurred by drifting particles, and hear the muffled crunch of frozen ground underfoot. The cold is dry, sharp, and invigorating, conditions that many Ice Age mammals evolved to exploit. These vast steppes are not barren. They are, in fact, highly productive ecosystems. The cold, dry conditions favor grasses that store energy in roots and underground tissues, allowing them to survive both freezing temperatures and grazing pressure. The resulting plant-herbivore cycle supports enormous biomass. This is why mammoths thrived for hundreds of thousands of years despite living in cold climates. The steppe grasses were rich in nutrients, and the environment, though chilly, was dependable. Snow seldom accumulated deeply, thanks to constant winds, allowing animals to graze year-round. The presence of these megafauna also contributes to the climate system. Large grazing animals disturb snow cover, exposing bare ground that absorbs more sunlight, slightly warming their local environment. They break up soil crusts, encouraging certain grasses to grow. In some ways, their ecological engineering may have helped maintain the steppe ecosystem against encroaching shrubs and forests when climates briefly warmed. In this era, animals and climate dance together. The cold creates the habitat sustains the animals maintain the habitat. Humans, when they eventually arrive in the mammoth steppe tens of thousands of years after its formation, become another part of this web. But at this point in our story, long before Homo sapiens spreads across Eurasia, the steppe is ruled entirely by the giants of the Ice Age, shaped by the winds and sustained by the deepening cold. The winds themselves undergo dramatic transformations as glaciation deepens. The massive domes of ice create immense pressure systems that alter atmospheric circulation. Cold air sinks over the ice sheets, forming persistent high-pressure systems that steer wind patterns southward. These winds strengthen the mid-latitude westerlies, fast-moving air currents that circle the planet. In a glacial world, the westerlies intensify, shifting storm tracks downward across continents and generating frequent storms that sweep dust, snow, and cold air across vast distances. In addition to shaping ecosystems, these winds influence the global climate through the movement of dust. Dust lofted into the air settles onto ocean surfaces, feeding phytoplankton, strengthening carbon uptake, and reinforcing global cooling. Some of the dust falls on the ice sheets themselves, forming thin gray layers. Although dust darkens the ice slightly, the chilling power of dust-laden skies far outweighs any localized warming these layers might cause. As the winds grow stronger, deserts expand. In southern Africa, Australia, and Central Asia, sparse vegetation yields to salt flats and dunes. Rivers shrink or shift course, lakes dry into basins of cracked sediment. These deserts become colossal dust sources, feeding the atmosphere with fine particles that travel between hemispheres. The Sahara, in particular, becomes a dust-emitting engine, its expansion driven by weakened monsoons and cooler temperatures. Loess deposits, huge blankets of wind-blown silt, accumulate across long belts in Europe, Asia, and North America. Some grow as thick as multi-story buildings, preserving a detailed record of glacial-era winds that still stands today. Farther south, ecosystems reorganize in other ways. Tropical regions cool as well, though less dramatically, allowing montane glaciers to expand in the Andes and East African highlands. Rainforests contract slightly, making room for savannas and seasonal forests. In regions like the Amazon, habitat fragmentation shapes evolutionary paths for countless species. Even near the equator, the fingerprints of glacial cooling appear. Lower sea levels expose land bridges. Coral reefs decline in some regions due to cooler waters. Upwelling intensifies along certain coasts, bringing nutrients from the deep. At the edges of the ice sheets, life is harsh. Frozen ground extends far south, forming permafrost, soil that remains frozen year-round. This frozen earth stretches across Eurasia and North America, altering drainage patterns, trapping ancient vegetation below its icy surface, and shaping the landscapes that future humans will eventually walk. When the summer sun is too weak to thaw the uppermost soil layers deeply, entire ecosystems adapt to shallower roots and brief growing seasons. In this world, seasons grow extreme. Winters bite harder and last longer than anything familiar today. Summers, though cool and brief, burst with plant growth, fed by the long hours of sunlight at high latitudes. These are the conditions that allow massive herds of herbivores to survive, even flourish, despite the cold. Amid all this change, a deep truth emerges. Life does not merely endure glacial conditions. It reshapes itself to flourish within them. The giant mammals that stride across the steppes, the winds that sculpt the plains, the dust that swirls through the skies, the glaciers that grind mountains into powder. Together, they form a portrait of a planet transformed. The glacial world is not an empty frozen wasteland, but a rich and vibrant ecosystem built on the edge of extreme conditions. As we close this section, imagine standing on the mammoth steppe beneath pale skies streaked with windblown dust. The distant ice sheet gleams like a wall of white. Herds rumble across the frozen ground. Winds whistle across ridges and valleys. The planet is alive in its own stark way. Alive with giants, alive with movement, alive with cold. And all these forces, bound together, continue steering Earth toward the deepest phase of its 100,000-year freeze. By the time the world is fully locked into its icy mode, its winds sharpened, its oceans reorganized, its megafauna roaming vast frozen steppes, the glacial system has become something far stranger and more dynamic than a simple story of steady cooling. For although ice sheets take tens of thousands of years to grow, they do not always advance at a smooth, predictable pace. Instead, researchers studying ancient sediments, ice cores, and landforms uncovered an unexpected truth. Glaciation often unfolds in powerful pulses, bursts of rapid ice growth that occur even when orbital changes themselves are slow and gentle. These surges, sometimes called glacial pulse events, stand at the heart of the Ice Age mystery, revealing how a seemingly sluggish climate system can suddenly accelerate, transforming continents not over millennia, but over centuries. To understand these pulses, imagine an ice sheet thousands of kilometers wide and more than 2 kilometers thick. Ice of such magnitude is not a rigid block, it is a living, flowing mass, constantly reshaping itself under the influence of gravity, snowfall, and the slow rearrangement of heat around the planet. As it grows, the ice thickens at its center, adding weight that pushes outward. This weight reduces friction at the base, especially when meltwater seeps beneath the ice, allowing glaciers to surge forward. When conditions align, an ice sheet does not merely expand, it lurches, advancing tens or even hundreds of kilometers in comparatively short bursts. Scientists studying the Laurentide ice sheet found evidence of multiple such surge events. Some were triggered by climatic shifts, others by internal ice dynamics, and still others by interactions with the underlying geology. For example, when a thick ice dome depresses the crust beneath it, the lowered land becomes colder, allowing more snow to accumulate. This can initiate a feedback loop. The ice pushes the crust down, the lowered crust cools further, snow piles up faster, the ice thickens more quickly. Once the weight reaches a critical point, friction thins beneath the sheet and the glacier accelerates. But surges do not only come from below, they come from above as well. During glacial periods, dust in the atmosphere increases dramatically. Dust can cool the planet, but when deposited on ice, it can also darken its surface. In small amounts, this can hasten melting, but in most cases, the dust is quickly buried under new snowfall and becomes irrelevant. What matters more is dust's influence on the oceans. Iron fertilization enhances carbon dioxide drawdown, which amplifies cooling. A sudden intensification of dust storms may therefore trigger enhanced oceanic CO2 uptake, causing temperatures to plummet more quickly than the orbital cycles alone would predict. Such rapid cooling can stack year after year of snow accumulation onto ice sheets that were previously growing only modestly. One of the most dramatic examples of glacial pulses comes from what scientists call rhythmic events. These are episodes during which massive armadas of icebergs broke off from the Laurentide ice sheet and drifted into the North Atlantic, releasing vast quantities of rock and sediment into the ocean as they melted. Rhythmic layers, thick bands of ice-rafted debris, appear repeatedly in Atlantic sediment cores. While these events mark catastrophic ice loss, paradoxically, they are usually preceded by episodes of very rapid ice growth inland. The surging of the ice sheet toward the coast destabilized it, leading to calving episodes of extraordinary scale. In other words, the system oscillated internally. The ice grew quickly, destabilized, collapsed outward, and then recovered as cooling continued. Another pulse mechanism involves atmospheric circulation reorganizations. When ice sheets grow large enough, they disrupt the jet stream so dramatically that storm tracks shift for thousands of kilometers. A new storm path might bring heavy snowfall to a region previously receiving little, suddenly accelerating glaciation in that zone. Conversely, a region once favored by snowfall might become starved of moisture, halting its glacial growth even though temperatures are still falling. These internal reorganizations can produce highly uneven, rapid ice advances across a continent. Even small changes in ocean circulation can ignite glacial pulses. When the Atlantic overturning circulation weakens, something that often happens during early and mid-glacial phases, the North Atlantic cools suddenly and sharply. This cold snap encourages more sea ice, stronger winds, and expanded snowfall along continental margins. A single century of ocean-driven cooling can produce enough new snow to thicken an ice sheet significantly. This thickening then triggers the next phase of glacial advance. What makes glacial pulses especially remarkable is their speed. Though the overall glacial cycle spans tens of thousands of years, certain advances appear to have unfolded within a few centuries, or in some cases, within mere decades. Landforms known as moraines, ridges of debris pushed forward by glaciers, show episodes of fast advance followed by stabilization. Ice core chronologies reveal abrupt temperature drops that coincide with periods of intense snowfall. Geological evidence from regions like the Great Lakes Basin, the North Sea, and Siberia indicate rapid ice advances that must have occurred far faster than orbital pacing alone would allow. These rapid pulses offer insight into the climate system's sensitivity. Once a glacial world reaches a certain threshold, once ice sheets are sufficiently large, CO2 sufficiently low, oceans sufficiently stratified, and winds sufficiently intense, the system becomes capable of self-accelerating change. The climate is no longer responding solely to orbital forcing, it is responding to its own internal state. Orbital cycles set the rhythm, but the planet's internal dynamics compose the melody. A similar dynamic appears in the phenomenon known as Dansgaard-Oeschger events, which are sudden dramatic temperature fluctuations recorded in Greenland ice cores. Though typically associated with warming pulses, these events demonstrate how abruptly climate can shift, even in glacial periods. In some instances, the North Atlantic warmed by as much as 8-15 degrees Celsius in only a few decades. While these events are warming spikes, they highlight the underlying instability of the glacial climate, instability that can just as easily manifest as sudden cooling when conditions favor it. Ice sheets themselves possess rhythms that emerge only when they grow large enough. These rhythms are governed by the balance between snowfall accumulation and ice flow, by the thickness of the ice, by the temperature at the base, and by how easily ice slides over bedrock or mud. Even without significant external forcing, an ice sheet can cycle through phases of thickening and sudden advance, much like a heartbeat that strengthens or weakens depending on conditions internal to the body. These glacial pulses help explain why ice ages do not resemble smooth curves in the geological record. Instead, they look jagged, sudden drops, brief rises, rapid transitions, and prolonged plateaus. The ice sheets surge, pause, reorganize, collapse slightly, then surge again. The climate oscillates underneath them. The ocean and atmosphere respond, feeding energy into the process or withdrawing it. In this dynamic interplay, the glacial world becomes a place of powerful, unpredictable, and often violent shifts, despite the slow pace of underlying orbital cycles. As this section settles into its final image, imagine Earth not as a slowly freezing sphere, but as a restless, shifting organism. Ice sheets breathing in deep pulses, oceans rearranging currents, winds strengthening and swirling over transformed landscapes. Sudden glacial surges carve new valleys and extend white plains across continents. Icebergs break free in armadas that darken the Atlantic. And deep beneath the surface, sediments collect in layers that future scientists will one day read as records of these surging, pulsing rhythms. The planet's deep freeze is not smooth. It's alive with sudden motion, driven by forces ancient and immense. The glacial world, having descended through tens of thousands of years of cooling, sits now in its deepest phase. Vast ice sheets towering kilometers high, oceans dark and stratified, winds roaring across dust-laden plains. For a long stretch, Earth remains locked in this cold equilibrium. But eventually, slowly at first and then unmistakably, warmth begins to push back. It begins not with any dramatic eruption or sudden surge of heat, but with the quiet shifting of sunlight, orbitally timed pulses of increased summer energy that start unraveling the cold machinery piece by piece. This is the moment when warmth fights back, reasserting itself against the immense inertia of the Ice Age world and preparing to bring the glacial chapter to a close. The seed of every glacial termination lies in the same place where every glacial beginning is born: northern summer sunlight. When orbital cycles realign, when obliquity rises, when precession swings northern summers toward perihelion, and when eccentricity amplifies these effects, the summer energy at high northern latitudes begins to increase, not all at once, not dramatically, but consistently, year after year, century after century. At first, the ice barely notices. But as this uptick persists, the balance that once favored accumulation begins to tilt. Imagine the far northern latitudes under this gradually strengthening sun. Snow still falls heavily in winter, but summers begin to linger a bit longer. Heat penetrates a little deeper into the snowpack. Meltwater forms broader pools on glacier surfaces. Streams cut channels into ice that had remained solid for millennia. These meltwater channels deepen and widen each summer, carving pathways that weaken the glacier's internal structure. The energy difference is not large, perhaps just a few tens of watts per square meter above glacial lows. But in a climate system as delicately balanced as Earth's, this small shift begins to crack the stability of the ice sheets. The first response of the ice sheets is usually surface melt, not wholesale collapse, but thinning. This thinning often begins at the margins, where warmer air and exposed land accelerate melting. But the transformation picks up when meltwater reaches the glacier bed. Water at the base acts as a lubricant, reducing friction between the ice and the rock. Pockets of meltwater expand into networks of subglacial channels. The ice, no longer bound tightly to its bed, begins to slide more rapidly. Retreat accelerates. As northern summers grow stronger, two large-scale processes deliver additional warmth: increased insulation from rising axial tilt, precession bringing northern summers closer to perihelion, making them more intense. When these two align, the effect is potent. Northern lands receive more sunlight, not by a small amount, but by enough to make the difference between persistent snow and rapid meltwater runoff. One of the earliest signs that a glacial period is waning appears in the oxygen isotopes within ice cores from Greenland and Antarctica. These records show sharp spikes in temperature, sometimes rising 5–10 degrees within just a few centuries, as summer insulation crosses the threshold needed to destabilize ice sheets. At the same time, ocean sediment cores show changes in deep-water carbon signatures, indicating that the deep ocean begins releasing CO2 back to the atmosphere as warming loosens the stratification that held it in place. This atmospheric CO2 increase amplifies warming. As the ocean begins to mix more vigorously, carbon-rich deep waters rise to the surface, releasing stored CO2 that had been trapped for thousands of years. Once released, this CO2 strengthens the greenhouse effect, reinforcing the warming initiated by orbital changes. Thus, just as the ocean played a crucial role in deepening glacial cold, it now becomes a key engine of deglaciation. Melting ice sheets also affect sea levels. As melt accelerates, sea levels begin to rise, not slowly but in increasingly rapid pulses. Early in a termination, sea levels may rise only a few meters over centuries, barely noticeable on a planetary scale. But as feedbacks intensify, meltwater surges cause sea levels to climb by tens of meters in relatively short intervals. Geological records show that during some terminations, sea levels rose by more than 20 meters over just a few thousand years, a dramatic shift that redrew coastlines worldwide. The melting ice sheets, in turn, reshape atmospheric circulation. As the massive cold air dome over the Laurentide ice sheet weakens, the jet stream shifts northward. Storm tracks migrate, winters lose some of their ferocity. Winds carrying dust diminish as vegetation slowly reclaims the steppe. Dust levels in ice cores begin to fall, marking another signal of global warming. These atmospheric and ecological shifts happen gradually, but once begun, they reinforce each other. Less dust means less sunlight is scattered away from Earth, allowing more warmth to reach the surface. Expanding vegetation darkens land surfaces, reducing albedo. Each of these small changes nudges Earth toward warmth. One of the most surprising aspects of glacial termination is how asymmetric it is compared to glacial growth. While ice sheets take tens of thousands of years to build up, they often collapse within a few thousand. The melting phase runs on a different set of feedbacks, driven by powerful amplifiers such as rising CO2, falling albedo, and rapid ice flow dynamics. The terminations are abrupt relative to the long, slow buildup of ice. This asymmetry is one of the signature features of the glacial cycles recorded in deep-sea sediments. Take termination 2, around 130,000 years ago, which ushered Earth into the warm Eemian interglacial. It began with strengthened northern summer sunlight and quickly cascaded into a global warming pulse. Ice melted rapidly. CO2 rose from around 190 to 270 ppm. Sea levels climbed, eventually resting 6.9 meters higher than today. A similar pattern unfolded during termination the Wenor, about 11,700 years ago, which ended the last glacial period and began the Holocene, the warm interval in which humans have lived ever since. As warmth fights back, ecosystems reorganize just as dramatically as they did when cooling first began. Grasslands contract, forests surge northward, rivers swell with meltwater, permafrost thaws in patches, loosening ancient soils and releasing trapped carbon and methane. The mammoth steppe begins to shrink. Megafauna migrations shift, pressing species into new territories. And with this ecological upheaval comes the arrival of Homo sapiens into landscapes reshaped by warming, a point in the distant future relative to the story we are telling in glacial time, but one that marks another turning of Earth's climatic wheel. Yet none of this warming unfolds uniformly. The climate system remains jittery and unstable during the early phases of a termination. Sudden cold reversals, like the Younger Dryas just 12,900 years ago, interrupt the overall warming trend. These are reminders that even as warmth rises, the glacial world resists collapse, clinging to its structurally entrenched cold wherever it can. But the long-term trajectory remains clear. The orbitally driven insolation increase overwhelms the feedbacks that once favored ice. With each passing millennium, warmth gains ground. The ice sheets thin, retreat, fracture, and eventually give way. Oceans rise, winds calm. Dust settles, forests reclaim the land, and Earth transitions from a frozen world into an interglacial oasis. As this section drifts into stillness, imagine the first strong summers returning to the far north, melting channels through walls of ice older than civilization, loosening the grip of winter that has held for tens of thousands of years. Warmth has begun its slow triumph over cold, setting the stage for one of the most dramatic sequences in Earth's climate tale, the violent collapse of ice sheets and the meltwater chaos that follows. Ice that took tens of thousands of years to build can vanish in a geological instant, leaving behind floods of almost unbelievable scale. This is the stage where Earth's long freeze unravels in violent beauty. Rivers bursting with glacial torrents, proglacial lakes draining catastrophically, coastlines drowning beneath rising seas, and ocean circulation jolted into new patterns as freshwater floods the saltwater world. It is here that the planet transitions irreversibly from a glacial giant to a warming interglacial world. To picture the beginning of this meltwater chaos, imagine the margins of a massive ice sheet, say the Laurentide ice sheet, softening under increasingly intense summer sunlight. Water pools on the surface, forming wide, dark melt ponds that absorb even more heat than the surrounding ice. These ponds drain suddenly through cracks, plunging water to the glacier bed, lubricating and destabilizing enormous slabs of ice. The glacier begins to surge, advancing and retreating unpredictably along its edges. Some regions fracture into chaotic fields of crevasses and ice cliffs. Others collapse internally as meltwater hollows out subglacial caverns. At the same time, meltwater begins to accumulate in vast proglacial lakes, immense bodies of freshwater trapped between the retreating ice and the land. These lakes are not small. Some stretch hundreds of kilometers, rivaling modern inland seas. The most famous of these is Glacial Lake Agassiz, a freshwater titan so large it held more water than all the Great Lakes combined. For long stretches, the shrinking ice sheet dams these lakes, but ice is an unstable dam. It cracks, thins, and gives way abruptly. When these ice dams fail, the result is catastrophic. Water pours out in sudden, unstoppable floods that carve new valleys in days, reshape river systems, and send massive volumes of freshwater into the world's oceans. These floods leave behind scoured landscapes, giant ripple marks, and deep channels like the channeled scablands in North America, evidence of megafloods that once raged with volumes equal to hundreds of Amazon rivers combined. When this freshwater reaches the oceans, a second chaos unfolds. Cold, fresh water is lighter than warm, salty water, and as it pours into the North Atlantic, it disrupts thermohaline circulation, the global ocean conveyor belt. The Atlantic meridional overturning circulation can weaken sharply when flooded with fresh water, causing heat that once flowed northward to stall. For decades or even centuries, this sudden disruption can trigger abrupt cooling in the northern hemisphere, even as ice sheets continue melting. This mechanism is behind climate anomalies like the Younger Dryas, when the North Atlantic region plunged back into near-glacial cold for 200 years despite the overall warming trend. Meltwater pulses come in waves. During the last deglaciation, one of the most famous was Meltwater Pulse 1A, around 14,600 years ago, when global sea levels rose between 14 and 18 meters in just a few centuries. Another, Meltwater Pulse 1B, followed a few thousand years later with additional rapid rises. These pulses dramatically reshaped continental shorelines. Coastal plains vanished underwater, estuaries expanded, islands formed where there had once been connected land. Thousands of kilometers of coastline shifted inland in human timescales, an unimaginable transformation for people living through it. As sea levels rose, the great ice sheets destabilized further. The collapse of marine-based ice sheets, those with their bases below sea level, was particularly dramatic. When warm ocean water infiltrated beneath floating ice shelves, entire segments of ice could break off in massive calving events, creating fleets of icebergs that drifted across northern oceans. These armadas of ice transported boulders and sediments far from their origins, dropping them into the sea as they melted, leaving behind geological markers known as dropstones. Sediment cores from the North Atlantic are punctuated with these layers of debris, each layer a timestamp of massive iceberg releases. In Antarctica, similar processes occurred. The southern continent did not warm as abruptly as the north, partly due to the bipolar seesaw in ocean circulation, but as global temperatures rose, Antarctic ice shelves began to thin and weaken. The collapse of these shelves allowed land-based ice to flow more rapidly into the sea. Meltwater from the south contributed to global sea level rise, though the timing differed from events in the north. The combined effect from both hemispheres was a near-synchronous rise in sea levels toward the end of each glacial period. The landscapes left behind by these meltwater catastrophes are some of the most dramatic features on Earth. The deep fjords of Norway and British Columbia, carved by glaciers and drowned by rising seas. The vast Hudson Bay Basin, once the center of the Laurentide ice sheet, now a shallow inland sea. The English Channel, once a dry river valley, flooded by glacial meltwater to separate Britain from Europe. The Baltic Sea Basin, which transformed from a glacial lake into the brackish sea we know today. Beyond the physical destruction and creation of landscapes, meltwater chaos had profound impacts on climate feedbacks. As ice retreated, dark land and ocean surfaces absorbed more sunlight, accelerating warming. Vegetation surged into newly exposed areas, replacing tundra with forests and lowering albedo even further. Rivers, swollen with meltwater, carried nutrients into the oceans, stimulating bursts of marine productivity and affecting carbon cycles. All these changes amplified the warming already underway. Meanwhile, the atmosphere responded rapidly. Dust levels fell sharply as soil stabilized under fresh vegetation cover. Greenhouse gas concentrations rose as warming oceans released CO2 and as thawing permafrost emitted trapped carbon and methane, a feedback that contributed still more warmth. The climate system, once locked in a cold equilibrium, now swung toward warmth with accelerating force. But even as the glacial world collapsed, the process was uneven. Some ice sheets retreated in fits and starts, others remained stable for centuries before suddenly giving way. Climate oscillations punctuated the warming, with brief cold reversals interrupting otherwise rapid deglaciation. This uneven retreat is why coastlines rose in stair-step patterns rather than a single smooth curve. Still, the long-term direction was irreversible. Once the summer sunlight crossed the critical threshold, once CO2 rose and vegetation expanded, once warm water infiltrated glacial margins, the ice sheet's fate was sealed. Their collapse, violent, messy, and world-altering, could not be stopped. As this section softens toward its close, picture the world in this moment of profound transition. Meltwater roaring through glacial valleys, seas rising into once-distant shorelines, continents reshaped beneath the weight of ancient ice releasing its hold. A planet emerging from its deep freeze does so not quietly, but with a cascade of floods and storms, a shuddering rearrangement of land and ocean that sets the stage for the warm interglacial Earth we know today. At last, the long arc of the Ice Age cycle bends toward its final movement, not an ending but a return to the beginning, because the story of Earth's glaciations is not a straight line, but a loop, a cosmic rhythm that rewrites itself every 100,000 years. After meltwater pulses roar across continents and the ice sheets crumble into the sea, the planet settles into a new warmth, an interglacial, brief and bright compared to the long stretches of cold that came before. But even in this warmth, the seeds of the next deep freeze are quietly planted. The same orbital forces that once tipped Earth toward melting will, in time, tip it back toward snow that refuses to melt. And so the great cycle, eccentricity, tilt, precession, albedo, ocean carbon, winds, ice, meltwater, begins anew, repeating through millions of years with a patience that no human lifetime can witness directly. This final section lingers here, in the gentle sunlight of an interglacial world, and looks forward to why Earth freezes every 100,000 years, and why it will continue to do so for as long as the cosmic clock keeps turning. As the ice sheets retreat at the end of a glacial period, the planet's surface transforms dramatically. Bare, scoured land emerges from beneath ice that has lain there for tens of thousands of years. Rivers find new channels, lakes fill basins carved by ancient glaciers, vegetation surges into newly exposed areas, first tundra, then shrubs, then forests. The mammoth steppe collapses, megafauna migrate into shrinking cold refuges. Some will survive the new warmth, others will not. Dust levels fall as soils stabilize and moisture returns, the atmosphere clears. The ice sheets that once shaped wind patterns, storm tracks, and ocean circulation gradually lose their grip on the climate. Yet amid this warming, a subtle shift occurs. The orbital cycles keep moving. The rising tilt that helped melt the ice will eventually begin to fall again over its 41,000-year swing. Precession, which currently aligns northern summers with higher energy, will drift until those summers occur farther from the sun. And eccentricity, the longest cycle of all, will eventually bend Earth's orbit into a more elongated shape again, changing the contrast between seasons. These cycles never stop. They never rest. They continue tracing their ancient patterns through the starlit void, indifferent to the rise and fall of species below. Even today, in the Holocene, the interglacial that began 11,700 years ago, these cycles are still moving. Northern summer sunlight has been slowly decreasing for several thousand years due to precession and tilt trends. If Earth's atmosphere had remained as it was before industrialization, the planet would likely be heading toward the earliest stages of renewed glaciation over the next several thousand years. It would not happen tomorrow, nor in a human lifetime, but the slow decline of northern summer insolation would eventually cross the threshold again. Snow lingering, forests retreating, tundra advancing, and the first seeds of future ice sheets forming in the far north. The cycle would begin again exactly as it has for the last million years. But Earth's climate system is not merely driven by orbital cycles, it responds to them with amplifiers. And these amplifiers, once set in motion, ensure that the freezing occurs in a pattern we can recognize in the geological record. Slow descent into cold, rapid warming, and long stretches of interglacials shorter than the glaciations they interrupt. For the last 8 glacial cycles, this pattern has held remarkably steady, roughly 90,000 years of cold, followed by 10,000 to 15,000 years of warmth. The warmth is fleeting compared to the cold, yet it is during these brief intervals that life surges, forests return to high latitudes, sea levels rise, and climates stabilize enough for complex ecosystems and eventually human civilizations to flourish. The persistence of this pattern raises a deeper question. Why 100,000 years? Why does Earth freeze with this specific frequency instead of, say, every 41,000 years as it once did earlier in the Pleistocene? The answer lies in the interplay between orbital cycles and the evolving sensitivity of Earth's climate. Around 1 million years ago, ice sheets grew larger and more stable due to long-term cooling, lower baseline CO2 levels, and tectonic shifts that altered ocean currents. These larger ice sheets needed more summer energy to melt, so much more, in fact, that the 41,000-year tilt cycles alone were no longer sufficient. Only when the 23,000-year precession cycle aligned with eccentricity peaks, creating truly powerful northern summers, could the ice sheets collapse. Thus, the climate synchronized to the longer eccentricity-paced rhythm. It is not that eccentricity itself directly drives huge temperature swings. Rather, the climate became more responsive to those rare moments when tilt and precession were amplified by eccentricity into melt-triggering energy peaks. This eccentricity pacing explains the structure of the last 1 million years of glacial cycles. Each cycle is shaped by the same components: orbital forcing, setting the timing; albedo feedback, amplifying cold; ocean CO2 drawdown, reinforcing cooling; dust and dryness, intensifying glacial conditions; ice sheet feedbacks, causing pulses of growth and collapse; meltwater events, destabilizing circulation and accelerating warmings. These processes intertwine into a repeating climatic heartbeat, too slow for humans to perceive without the aid of geological records, yet precise enough that the rhythm stands out clearly in deep-sea sediments spanning millions of years. Each heartbeat ends with a deglaciation, like the one that brought us into the Holocene. Each begins with declining northern summer sunlight thousands of years after interglacial warmth peaks. In the present day, the natural trajectory of this cycle collides with something unprecedented: human influence. Greenhouse gas levels have risen far beyond glacial-interglacial ranges, reaching values not seen for millions of years. This additional warming has overwhelmed the subtle cooling trend Earth would otherwise be experiencing from orbital cycles. In other words, the next glacial cycle has been delayed. Climate models and paleoclimate reconstructions suggest that even if emissions cease tomorrow, the elevated CO2 currently in the atmosphere may be enough to postpone the next ice age for tens of thousands of years, possibly longer. It is a moment unique in Earth's long history. The ancient rhythm continues, but the climate no longer follows it as it once did. And yet, the orbital cycles themselves, the cosmic clock, remain unchanged. For as long as Earth circles the Sun, eccentricity will stretch and relax its path. Precession will turn the axis. Obliquity will rise and fall. These cycles are woven into the mechanics of the solar system, indifferent to the climate they influence. One day, when greenhouse gas concentrations eventually fall, whether through natural processes or through forces we cannot yet foresee, the planet will once again respond to the orbital whispers. Northern summers will weaken, snow will linger, and the first thin patches of unmelted whiteness will appear on the high plateaus of the far north, just as they once did long before humans existed. The cycle will start again. As this final section drifts toward its ending, imagine Earth not in a single moment but as a world breathing through vast stretches of time. Exhaling warmth, inhaling cold, shifting slowly between states defined by the faint geometry of its orbit. The continents rise and fall beneath the weight of ice. Oceans expand and contract. Winds reshape the land. Life adapts, flourishes, migrates, transforms. Civilization emerges in a brief warm window. And all the while, the great 100,000-year cycle continues. Earth freezes with ancient regularity not because of catastrophe, not because of cosmic accident, but because it dances to a celestial rhythm, a rhythm woven into its orbit, amplified by ice, oceans, dust, and air, and written into the memory of stone, sediment, and ice. As long as the planet spins through space, that rhythm endures, and so the story closes gently, with Earth resting in the warmth of an interglacial sun, knowing that in the deep future, when the orbital clock turns once more, the cold will return. Not as an end, but as part of the endless cycle that shapes the life of our planet.